The last video I explained about the applications of sound. Now in this video, and this video will conclude the videos on waves, and then I will explain you about heat. So my last video on waves is about the Doppler effect. So what's the Doppler effect? Now you may have seen this. Actually Doppler effect is another application of sound, in fact. So you may see, now if you are stationary at some place and say a car is moving towards you, or a train, or a train is better because it emits some sound. So when a train is approaching you, you may have seen that when the train is approaching you, the sound of the train is high, and when the train is leaving you, you may have seen that the sound is diminishing away. So what's the reason as to why we have different sound? Because you are stationary and the same train is moving towards you and then on and away from you. So what's the reason as to why this happens? So that is the reason, that is the cause as explained by the Doppler effect. So the Doppler effect, sometimes called the Doppler shift, is a change in frequency of emitted waves produced by motion of an emitting source relative to an observer. So Doppler effect states that this change of sound is due to the change of frequencies and hence the change of wavelengths. So actually it happens due to the change of wavelengths. So if you take a source that is moving towards an observer, each successive wave is emitted from a position closer to the observer than the previous wave. Now you know that when the train is approaching you, that the distance, now if the first wave is emitted at a distance of 4 meters, the second wave is emitted at a distance of 3 meters. The distance between the second wave and the observer is less than that of the distance between the first wave and the observer. So what generally happens is that you can hear that the sound is much high, or the intensity is high, when the train or the object in which the sound is emitted is approaching you. So in the case when the source is moving away from the observer, you can see that the waves spread out and the sound diminishes in intensity. So when the train moves out from the observer, what generally happens is that the sound waves, the distance the sound travels within a unit time, increases as the train proceeds away from you. So if the train is initially at a distance of 3 meters away from you, at the next second, if the train is 5 meters away from you, the distance the sound has to travel through the air to you is high, and then at a meter of 10 meters from you, away from you, the distance the sound has to travel away from you is high. So sound is not propagated through a constant medium. Sound is just propagated. Sound is not propagated as like in the case of strings, you have some frequency, not like in that case. Sound is just propagated to the air, not towards you with some constant frequency. With frequency, just the sound is emitted to the air. So the sound, as I mentioned in the case of applications of sound, excuse me, and in the case of applications of sound, the sound waves, the intensity of sound waves diminishes as the radius or the distance between the two observers, the source and the observer, increases. So the larger the distance between the source and the observer, the lesser the intensity of sound. So when the train is moving away from you, the distance between the train and you is increases with time. So the sound wave diminishes because its intensity diminishes. So the observer experience, now you can also show that this in a graphical manner. So if you take a car like this, now if the car is emitting sound in this direction, I may choose two observers like this. One observer in a direction so that the car is moving away from the observer, source moving away from the observer, and another observer in which the source is moving towards the observer. So the direction of sound is in this direction. So what generally happens is that this observer experience sound of increased frequency and hence decreased wavelength. So what generally happens is that this observer may hear a larger sound for the same frequency emitted by this source than this observer. So the frequency heard by this observer is low and the intensity is low, but the frequency heard here is large. So you know that the velocity of sound in air is a constant, So what generally happens is that when the frequency increases, the wavelength for such a wave decreases. So the wavelength here is decreased because of the decreased length between the source and the observer. So the wave pattern observed for such a sound wave is as follows. Now when the source is moving towards the observer, all the sound waves compact together. When the source is moving away from this observer, the sound waves diverge. Now so you can see that these are not compact, these are very relaxed. So what generally happens is the change of wavelength and hence the frequency. So when the source is at rest, you can see a symmetric symmetric concentric circles here. So the waves are not biased or elongated to a certain direction. So the wavelength at this point is the same as this point, and the wavelength at this point and is the same as this point. Now in the case when the source is in motion, you can say that as in this case the sound waves converge, or they get compacted together in the direction of the sound or the direction of the source, right? So different wave patterns can be formed. So when you increase the sound, now when you increase the sound say up to about 300 meters per second, these are very compact and beyond the maximum around. Now in the case of many aircrafts, Air Force aircrafts, high speed jets, you may have heard about sonic booms. So sonic booms happen when the velocity of a wave or velocity of the frequency emitted, or the velocity of the sound, right? Velocity of the sound, in fact, velocity of the sound emitted by a source is greater than the velocity of sound in air. So when that happens, you may have seen that you get some uneven curves in a conical shape, not in like this. So the maximum frequency at which you can hear, the maximum velocity you can hear is at the frequency of the velocity of sound in air. So at that moment, all these lines get into a single line. So these get further compacted together, and at some point they get converged into a single line, and beyond that you get conical curves in which you experience sonic boom. So I'll not explain about the sonic boom. So the next concept that I'll be explaining you is about the general equation of Doppler frequency, the Doppler effect. So the apparent frequency is the frequency in which you hear the sound, and F is the frequency in which the source generally, in reality, emits the sound. So you know that if the object is stationary, that the frequency or the frequency at which the sound is emitted is equal to the apparent frequency. But if either or both the source and the observer is moving, you can say that the apparent frequency is not equal to the real frequency, but to an integer or a fraction multiple of the frequency, the real frequency. So the apparent frequency is defined as the velocity, the ratio of the velocity of sound relative to the observer, and that relative to the source, and that ratio multiplied by, or taken the product by the real frequency. So velocity of sound relative to the observer and that relative to the source can be easily calculated using the principle of relative motion. Now a source moves with the velocity of v on the Earth's surface. So you can say that the velocity of the source relative to the sound is equal to the velocity of the Earth relative to the sound plus the velocity of the source relative to the Earth. So that's from the relative velocity concept. So the velocity of the sound relative to the Earth is c, and we negate this principle because we know the value only of the velocity of the source relative to the Earth, not the velocity of the Earth relative to the source. So we negate this term. So that is now equal to velocity of the source relative to the Earth, which is v. So the velocity of source relative to the sound, velocity of sound relative to the source is equal to c minus v, and that is in this direction. Now you know that the velocity of the Earth relative to the sound is greater than the velocity of the source relative to the Earth. So c minus v is positive, so this is in this direction. However, if the sound moves in a velocity that is greater than the velocity of sound relative to the earth, then you can hear sonic booms, because c minus b will be the negative, so the velocity of sound relative to the source will be in this direction, right? So the source will be moving in this direction in that case, and the sound will be moving in this direction. For most of these, we assume that the velocity of the source is less than the velocity of the sound. So c minus b is positive, so the velocity of both the velocity of the source and that of the velocity of the sound are both in the same direction. So if you now first of all, to conclude this video, I'll do a sample problem, right? So if you take a source, to explain you about the equation and the Doppler effect, so if I take a source that is moving at a speed of 30 meters to the east, and the observer is also moving to the east with a velocity of 40 meters per second, so you have to consider the direction as well, because you are taking the velocity, not the speed. And if the frequency at which the siren of the source emits its sound is 50 hertz, and assuming that the speed of sound in air is 340 meters per second, what is the frequency of the sound as experienced by the observer? So this is a very simple solution that you have to do using the Doppler effect. So you know the real frequency. Here you know the real frequency, so you have to find the velocity of sound relative to the observer and that relative to the source. So as I mentioned, you can easily calculate that using the relative velocity principle. So you know that the velocity of the source relative to the earth is 30 meters per second, and that is to the east, and the velocity of sound relative to the earth is 340 meters per second, and that is also to the east, because the sound is moving in the direction of. So what generally happens is that the velocity of sound relative to the source, as I calculated, is actually the difference between the velocity of sound relative to the earth and that relative velocity of source relative to the earth. So that will be finally 320 meters per second. And in a similar way, you can calculate the velocity of sound relative to the observer. So the velocity of sound relative to the observer is finally equal to the velocity of sound relative to the earth, and you have to take the difference that from the velocity of the observer relative to the earth. So that is equal to 340 minus 40, which is 300 meters per second. So we know the velocity of sound relative to the observer, so that we calculated here as 300 meters per second. We know here the velocity of sound relative to the source, so we calculated that as 320 meters per second. We know the actual frequency, which is 50 hertz. So from the Doppler effect equation, you can say that the apparent frequency is equal to velocity of sound relative to the observer divided by the velocity of sound relative to the source, and that the whole thing multiplied by the real frequency. So finally you will get 46.875. So that's it about the Doppler effect, and this video concludes the videos on waves. So my next topic would be on heat, and I'll begin a new introduction to the physics concepts on heat. So thanks for watching all these videos on waves, and do join with me on the concepts of heat as well. So thanks for watching this video, and see you soon.